Today we're going to talk about confidence intervals. When you collect a sample and you calculate the sample mean, you're usually not interested in the sample mean, but you use the sample mean to estimate what the population mean would be. Now there are two kinds of estimates that you can make. One is a point estimate, in which you guess a single number, like I think the mean is going to be 4, or 5.3, or 1344.2. The other kind of estimate is the interval estimate. The interval estimate is when we guess two numbers, a high number and a low number, and you say, well, I think it's going to be somewhere in this range. Like, I think that the mean will be between 2 and 8. A confidence interval is when we also estimate the probability that our guess is true. So there's a 95% chance that the mean is between 2 and 8, or there's a 99% chance that the mean is between 1 and 9. When we make a point estimate, the best point estimate we can make is using the sample mean. The sample mean is one number, that's one number that we need, and so we make it. The downside of a point estimate is that it's almost never right, but we hope that it's close. A confidence interval is when we make an interval estimate that when we apply this procedure over and over and over again, it's right 95% of the time. So here we have a population, and every second we're collecting a new sample. If it looks about 30 scores, and we calculate a sample mean. And the sample mean, you can see from sample to sample, it fluctuates a little bit. Here we have the distribution of sample means. If we were to do this an infinite number of times, these means would all line up on this normal distribution here. Now, the confidence interval is the low number here and the high number on the other side. And you can see that it straddles the true population mean of 100 most of the time. Every once in a while, though, it does not straddle it. And the sample, there it goes. The sample mean, there it goes again. The sample mean is blue, meaning that this procedure didn't work that time. 95% of the time, the confidence interval will contain the true population parameter, and 5% of the time, it won't. So here we can speed this up, and you can see that most of the time it's red, but every once in a while it's going to be blue. And there it goes. There it goes again. So how do we calculate a confidence interval, like a 95% confidence interval or a 99% confidence interval? Well, we use a formula. It turns out that the formula is really just the z-score formula, but we solve for the population parameter mu. But let's see how it works. So we have a particular percentage that we want. Let's say it's 95 or 99 or whatever. And we're going to use this formula. So let's actually just put in a number there. So we want the 95% CI, or confidence interval. And the confidence interval consists of our point estimate, the sample mean. And then it consists of a z-score, a particular z-score, and the standard error. So the z-score for the 95% confidence interval we can calculate by finding out, what is the z-score associated with a particular percent. So if we go 1 minus the percentage that we're interested in, and then we divide by 2, we're going to get 0.025. This z-score is associated with the bottom 2.5% of the normal distribution, and then we want another one that's associated with the top 2.5%, and you put that together, you've got the 5% in each tail and 95% in the middle. So we need to look up the z-score. What is the z-score associated with the bottom 2.5% of the normal distribution? So you can use Excel, like norm's INV function, and it'll give us negative 1.96. If we put in 97 and a half, or 0.975, we would get positive 1.96. It's not that number exactly, but that's usually it's close enough. Okay, so we're just going to plug in 1.96. Oh, here it is. So you can see that 1.96 contains the upper 2.5, and the negative 1.96 contains the bottom 2.5%. So we've got two tails there, and 95% in the middle. So if we plug in 1.96 into this equation, we've got our formula for the 95% confidence interval. So we take our sample mean, we take 1.96, the z-score, and we multiply by the standard error. And we either subtract this off or we add it to the sample mean. So here is the anatomy of a confidence interval. The confidence interval starts with a point estimate, the sample mean, and then we subtract off z times the standard error, and then we also add on z times the standard error. The z times the standard error occurs often enough that it gets its own name. It's called the margin of error. Now, when you say the margin of error, what you mean is the 95% margin of error. If you want some other kind of margin error, like the 99% margin of error or the 68% margin of error, then you'll have to say that. So when you just say it all by itself, what you mean by convention is the 95% margin of error. Okay, so if we take the sample mean and we subtract off the margin of error, what we get is the lower bound of our confidence interval, the lowest number. And then for the upper bound, we take the sample mean and we add on the margin of error. So let's say we want the 99% confidence interval. And so we want, what is the z-score that corresponds to the middle 99%, or we've got 0.5% of our normal distribution here and 0.5% over here, and it happens to be around 2.58. So if we plug that in right there, 2.58, and we get this. So the main part of calculating a confidence interval is to calculate or look up what z-score corresponds to the confidence interval, and then you'll calculate your standard error by taking the standard deviation divided by the square root of the sample size. Okay, so let's try one. So let's say the sample mean is 14, our sample size is 16, the standard deviation is 5. We're going to have to assume that the distribution was normal to begin with, and we're also going to calculate our standard error. So we take our 5 and put that right there, and take our sample size of 16 right there. Square root of 16 is 4. 5 divided by 4 is 1.2, so this 1.2 is going to go right there. And then we're going to look up our 5% z-score. It's 5% because it's 5% in each tail, adding up to 10%, so that the middle 90% is in the middle. So it's around 1.645. So we put that one in there. Now we're going to multiply these two numbers, and we get about 1.97. And there are two different ways that you can specify your confidence interval. You can take the sample mean and add and subtract your margin of error, or you can actually make these calculations. So 14 minus 1.97 is 12.03, and 14 plus 1.97 is 15.97. So we've got 14 plus or minus the margin of error, the 90% margin of error, or we can say that there's a 90% probability that the true population mean falls between 12.03 and 15.97. I'll pause to note that this isn't strictly true, as a number of people who do Bayesian statistics will be happy to tell you. To be more technically correct, one would say that 95% of the time that this procedure is applied, the true population mean will be contained in this confidence interval. But for our purposes, we can sort of fudge it a little bit and say there's a 90% probability that the true population mean falls between 12.03 and 15.97. The difference is subtle, but if you want to be a stickler about it, you can be. Okay, let's try another one. The sample mean is 200, sample size is 100, and now we don't actually have to make We don't have to assume that the original population is normal because our sample size is big enough for the z-score to work. Our standard deviation is 30, and we want the 95% confidence interval. So our population mean is going to be between these bounds. So let's calculate our standard error first. So we've got a 30 standard deviation, put that right there. Sample size of 100, put that right there. Square root of 100 is 10, 3. 30 divided by 10 is 3. So this 3 is going to go right there. And then we need to look up 1 minus 95% divided by 2. So 1 minus 90 is 95% is 5%. 5% divided by 2 is 0.025. And it's going to be 1.96. So we put in 1.96 times 3, and we put in our sample mean of 200 right there. And then we work out what the margin of error is going to be. And so we've got our margin of error is 5.88. So it's 200 plus or minus our margin of error of 5.88. Or we can work it out. 200 minus 5.88 is 194.12. And then 200 plus 5.8 is 205.88. So our nice and easy way, but not technically a correct way of thinking about it, is there's a 95% probability that the true population mean falls between these two numbers. So this is how we calculate our 95% confidence interval. Well, why would we calculate a confidence interval at all? Why would we stop at 95% or 90%? Don't we want to be 100% confident? And there's really only one way to be 100% confident, that your confidence interval goes from negative infinity to positive infinity. That way you'll never, ever, ever be wrong. Well, what's wrong with that? Well, to say that it's some number doesn't actually help anyone. There's no useful information in that. And to a lesser degree, the wider your confidence interval, the less informative it is. Like if the weather forecast said that the temperature is going to range somewhere between negative 100 degrees and 300 degrees, that's not useful information because that's going to be true pretty much all the time. And what you need is a narrow confidence interval. So if you want a narrow confidence interval, why don't you just do a point estimate? Well, the point estimate is I suppose useful in a sense, but it's almost always wrong. So these confidence intervals are a kind of compromise between being useful and being right. The more confidence, the wider your confidence interval needs to be. So a 90% confidence interval is narrower than the 95% confidence interval. So this 90% confidence interval has the virtue of being narrower, but it's not going to be right as often. This 95% confidence interval has the virtue of being right more often, but it's wider. And this is the trade-off we make. So with more confidence, we need larger and larger intervals. Certain intervals for a confidence interval are much more common than others. Probably the least common is the 68% confidence interval. It's kind of a weird number. Why 68? Well, it happens to be the z-score that corresponds to one standard error. So if you just want to calculate the confidence interval plus or minus one standard error, that's the 68% confidence interval. More commonly, confidence intervals are either 90%, 95%, or 99%. So here's our 90% confidence interval, our 95% confidence interval, and our 99% confidence interval. By far, the most common is the 95% confidence interval. If you say confidence interval without specifying which kind, it's the 95% confidence interval. So therefore, that z-score of 1.96, it's really important. It shows up rather often. And we already saw that it comes up often because it corresponds to the critical z-score in a two-tailed test with an alpha of 0.05. If all these calculations seem like a bit much, I have good news. We have a spreadsheet that will automate the process for you. So all you've got to do is know what the sample mean is, know what the standard deviation is, the population standard deviation, and you have to know what the sample size is and whatever confidence interval you want. So let's say that we wanted to calculate the 95% confidence interval, so I just put in 95 there, and I've got a sample mean of 14.8 and a standard deviation of 2.7 and a sample size of, let's say, 87. Here it has all of the formulas that it used to make all these calculations. The z-score that corresponds with the 95% confidence interval is 1.96. Our standard error is we take the standard deviation of 2.7, divide by the square root of 87, and then it's going to come out to be almost 0.3, 0.289. And then we multiply this times this, and we're going to get that. Our margin of error, 95% margin of error. We take our sample mean, subtract our margin of error, and we'll get the lower bound of our confidence interval. We take our sample mean and add the margin of error, and we're going to get our upper bound. So all these calculations are done for you automatically. At the bottom of this spreadsheet, there's another kind of confidence interval, confidence intervals with proportions. So during election seasons, you'll often see that news reports will say, well, candidate X has 53% of the votes with a margin of error of 4%. What they did is they calculated from polling data a margin of error around the proportion of people that voted for candidate X. So let's take a look at this. Proportions are variables that are either yes or no, or 1 or 0, or correct or incorrect, or something like that. Any kind of variable that has just two outcomes is something that we usually we can call a Bernoulli distribution or a binomial distribution. That wouldn't be on your exam or anything like that, but any kind of two-category variable we can calculate proportions with. So here we have a distribution that the true proportion is 0.9. So let's say we have a proposed law that's very popular in the population. 90% of the population agree that this new law should be passed. If you were to take different samples of the population, the sample data that wouldn't show exactly every time that the population that agrees with the law is 90%. It'll sometimes be above 90%. It'll sometimes be below, but it'll be hovering around 0.9. So what we'd like is a confidence interval around our sample polling estimate. So the formula that we've been using for confidence intervals so far is like this. It turns out that under the hood, proportions are no different, but the calculation is a little different. So everywhere you see a sample mean, we're just going to put P for proportion. And so the point estimate of our confidence interval is going to be the sample proportion, which is also it's a sample mean. And then we need the standard deviation of the proportion. And it turns out that the standard deviation is determined by the sample mean, or the proportion. So let's say it's 0.9, and we're going to say 0.9 times 1 minus 0.9. And then we divide by the sample size and take the square root of the whole thing. So what's nice is that the point estimate and the standard error it's determined by the same statistic, the overall proportion. So let's say that we want a 95% confidence interval if the sample mean, or the proportion that of people who want this new law, is 0.9, and let's say we poll 100 people. So the 95% confidence interval is 0.9 plus or minus, and the z-score that we look up for the 95% confidence interval is 1.96. And then we put in times the standard error. And so we take this P and we put in 0.9, and this P, 0.9. And then we take the sample size of 100 and put it right there. And we take the square root of this. And so we're going to get 0.9 plus or minus 1.96 times this whole thing here, and it's going to work out to be about 0.06. So 0.06 is our margin of error. So we say, well, it's 0.9 plus or minus 0.06, and when we work that out, it's going to be somewhere between 84 and 95%, 96%. So that is confidence intervals with proportions. So it turns out that confidence intervals has a one-to-one relationship with statistical tests. The 95% confidence interval contains all the information that you would need to conduct a two-tailed statistical test when alpha is 0.05. So since that's what we typically do, is two-tailed tests with alpha is 0.05, that 95% confidence interval, if you know it, then you've got pretty much all you would need to do a z-test. So here's our decision rule. If the value specified by the null hypothesis is in the 95% confidence interval, then we retain the null hypothesis. And if the value that is specified by the null hypothesis is outside the interval, then we will reject the null hypothesis. So if the null hypothesis says that the true population mean is 50, and we have a sample mean that leads to a 95% confidence interval of 56 to 50. Well, 56 to 50 does not contain 50. So this confidence interval is outside of, it doesn't contain this null hypothesis value. So I would reject the null hypothesis in this situation. So anytime your confidence interval falls outside of what the null hypothesis mean says it should be, then you would reject the null hypothesis. And for a lot of people, doing a z-test with confidence intervals makes a lot more sense than worrying about critical values and p-values and things like that.